right. Thank you. Yeah, it's a pleasure to be here. Such a international, different time zones, etc. Crowd. So the talk I'm going to give is perhaps not immediately within the realm of CRNs, chemical reaction networks, but there is some connection at a variety of places. So I hope to convince you of that. Let's see. So right. So R naught or that's the symbol used for the basic reproduction number. It's commonly used in population biology and epidemiology. So it finds its uses in mathematical biology more generally in that sense. When you talk to biologists, they'll give you a definition that's verbal. I'm not going to repeat it. I think it's a confusing definition. Instead, we'll focus on really a mathematical definition, and we'll investigate some of the properties of the basic reproduction number. And just to frame things without being defining notions. So in essence, basic reproduction numbers are proxies for the spectral abscissa of a linear operator. And the spectral abscissa is the real part of the rightmost eigenvalue of a linear operator on Rn. Okay. So if you don't understand this right now, that's fine. I hope to clarify this. And as an illustration, we'll use this basic reproduction number. And actually, I want to discuss something that perhaps is less relevant to this crowd, but more for people working in epidemiology. But I'll discuss a epidemiology model, very basic and simple one, that turns out can be modeled as a chemical reaction network quite straightforwardly. Okay, so here's the model. It's an SI model. S stands for susceptible individuals and I for infected ones. And so you have these differential equations. You see a mass action term here. You know, we'll talk more about this model, so it's not that important, but let me just summarize what the chemical reaction network would be, assuming mass action kinetics for this set of equations. So S plus I, if a susceptible and effective come together, they give two infectives. And there's some demography, so there's births of susceptibles, and then susceptibles and infectives can die, okay? Or, they could go to a different class of typically called recovered individuals, but let's think of them as death from this system at least. Okay, and so as I said, the last thing, perhaps this talk will stimulate some of you in the CRN community to explore the use of R naught. All right, so we need some math, and the first thing is a geometrical object. It's a proper cone in Rn. What do I mean by a proper cone? Well, first of all, it's a cone, which is a convex set that's invariant under scaling by non-negative numbers. So if I take a vector and I double its size, then I'm still in the cone. It's a closed set, so topologically, it's a closed set. It's solid, it's another topological property, means has non-empty interior. And it's pointed, meaning that the intersection of the cone with its reflection, negative C is just a reflection of the cone with respect to the origin, that intersection consists only of the zero vector. Okay, so some examples that are commonly used, and there's actually more, but I'll give two kind of classes. Is of course the positive orthant cone is the typical example, Rn plus, but any orthant cone would do. So these are vectors in Rn, so that the sign of xi multiplied by either plus or -1. So I'm going to raise -1 to the gamma I, and gamma I is either 0 or 1. So this means this expression is either xi or -xi, that is non-negative. These are examples of polyhedral cones, which are finally generated, and actually vice versa. More information in the footnotes here about what a polyhedral cone is and a finitely generated cone. It's quite straightforward, but it's not relevant really for the talk here. And then there's the Lorentz cone, or the ice cream cone, chicken model by this prescription here, which is not a polyhedral cone and not finitely generated. Here's a picture of it. It's really the ice cream cone that you think of when you're holding a cone of ice cream. All right, so this is in R3, but yeah, you can extend it to Rn if you want. And then the next notion is that of a dual cone, okay? A dual cone, just like in linear algebra, is really a dual vector. So it's a dual vector, it's a vector L in the dual of Rn, which we will identify immediately with Rn in the next step here, such that that linear functional is non-negative on the entire cone. So it's all those dual vectors that are non-negative when we evaluate them on the cone C. And because of the identification of linear functionals with inner products, thanks to the representation theorem, we can actually write that as, we can identify dual cones with subsets of Rn. And so these are the subsets, so that this is the standard inner product of y and x. Okay, so the inner product of y and x has to be non-negative for all points in the cone. And the dual cone consists of all those, you can think of them as row vectors, all the y's, whose dot product with any x in the cone is not negative. Turns out that dual cones are proper cones. It's a theorem, but you need to do a little bit of work. It's an actual proper cone. And in the two examples I mentioned on the previous slides, these are examples of self-dual cones. What I mean by that is that they can coincide with their dual cone. So any orthant cone has dual the cone itself. And any ice cream cone, its dual is, again, the ice cream cone. Or more generally, the Lorentz cone, same thing. Okay. So the first question one can ask is, given a proper cone, C, and now I'm going to look at differential equations. X dot is AX. So they're modeled by these matrices, or parameterized, I should say, my matrices A, linear operators, which A's have the property that when I start in the cone and I solve the differential equation, the solution remains in the cone forever. Okay. So the way to say this is which operators have the property that this semigroup, the semigroup of matrix exponentials, has a property that it preserves the cone. So if I apply this for any t to the cone, I'm still in the cone. Okay. Schneider and Vidyasagar actually considered this question in 1970. And I'll state the result in a moment, but I have to introduce one more concept, okay? And that concept is that of a cross-positive operator, given the cone C. So we say that an operator is cross-positive if whenever I pick a pair x and y, x in the cone and y in the dual cone, C star, and x and y are actually orthogonal, that's what this expression says, then the inner product of y with a times x, so this is x here, now here it's a times x, that inner product is non-negative. This is the definition of a cross-positive linear operator. Given a cone C, an operator is cross-positive on that cone if this condition holds. Here's the answer of Schneider and Vidyasagar, and they show that the semigroup preserving the cone is equivalent to cross-positivity of the matrix A. Okay. So if you apply this, for example, to the case where the cone is Rn plus, then a matrix is cross-positive if and only if its off-diagonal entries are all non-negative. So it's just the off-diagonal entries. You don't care about the sign of the of the diagonal ones. Only the off-diagonal ones have to be non-negative. Okay. Here's some very standard notation. Looks like a busy slide, but you're probably all very familiar with it. So to any linear operator on Rn, I'm going to associate 4 quantities. First one is the resolvent set. Second one is the spectral set, or the spectrum. Third one is the spectral abscissa, already mentioned briefly. And the last one is the spectral radius. Okay, the resolvent set is just those complex numbers so that this operator, lambda I minus A inverse, exists. Okay, so that happens, of course, we know when lambda is not an eigenvalue of the matrix A. The spectrum is the complement of the resolvent in the complex plane. The spectral abscissa is really the maximal real part over all eigenvalues. Okay, it's the maximal real part of all the eigenvalues. That's the spectral abscissa. And if I just take the modulus of the eigenvalues and take the largest one, I get the spectral radius of the matrix. Okay. So we probably all know spectral abscissa determines the stability of a differential equation x dot is ax, whereas the spectral radius would determine the stability of a discrete iteration given right here. Okay. Here's another important result from Schneider and Vidyasagar. So for a cross-positive matrix, we have that the spectral abscissa is in the spectrum. And even more, it has an eigenvector x that belongs to the cone. This is really an extension of the classical Perron-Frobenius theorem for cone-preserving maps. The extension goes here from cone-preserving maps to semigroups, operators of semigroups that preserve the cone. Okay. Here's another characterization, third characterization of cone-preserving semigroups. Actually, you know what? I'm going to skip it given time because I want to spend a little bit more time on the example. So the main theorem here is that I'll just do it very quickly. A being cross-positive, we saw that earlier, is actually equivalent to being what is called resolvent-positive. And very roughly speaking, resolvent-positive means that the resolvent operator maps the cone into itself, at least for those lambdas on some half-ray alpha to infinity. Okay. There's a lot extensive theory about resolvent positive operators. So this is yet another characterization of either cross-positive matrices or operators, or those that have operators that generate a semigroup preserving the cone. Okay, ready for basic reproduction numbers. Okay, so I'm going to do a thought experiment that may be hard to swallow, but first we'll address the question of why it's possible. But if I have an operator on Rn, linear operator, which is cross-positive on a cone, I can split it. Let's say I can split it in 2 pieces, f plus v, where the first piece is an operator that maps the cone into itself. The second piece is cross-positive on the cone. And moreover, this second piece has spectral abscissa, which is negative. It's a stable matrix, if you want. Okay. So then, if that is possible, we call this an admissible splitting of A. Okay. Now, there may be many admissible splittings of any given A. I may do this in a variety of ways. We'll see quickly that that's indeed the case. Okay. Well, if I now look at the following spectral radius, I take F, which is the first term, and then I take the opposite of V, and I take the inverse of it. You may ask, does that exist? Well, yes, actually you can. You can actually show that it is preserving the cone. So it's an operator that maps the cone into itself. Why that's the case obviously follows from the assumptions that I'm putting down here. But that needs a little argument. So these 2 operators inside here map the cone into itself. F does because of the assumption, and negative V inverse does because of what I say here. So their composition maps the cone into the cone. So that means that's it's also a cross-positive. I'm sorry. We can now look at its spectral radius. Okay. And there's a Perron-Frobenius theory for cone preserving maps. It says this spectral radius is an eigenvalue with a corresponding eigenvector in the cone. That is a basic reproduction number. And my title has a plural because there's many ways typically in which one can do the splitting. And each splitting yields a different value of R0. And I think in the epidemiology or mathematical biology world, this is not well enough appreciated, not appreciated well enough, and causes a lot of problems. But people think it's a unique quantity, but I tend to disagree. Okay, so do admissible splittings always exist? My answer is yeah, it does. So I'll give you one. I'll give you a whole slew of family of splittings. I'm going to write a given A, a constant A, parameterized as the following split, ft plus vt, where ft is t times the identity, and vt is A minus ti. Clearly, if I add f and v, I get A again, no matter what t is. But I'll assume t is bigger than the maximum of 0 and s of A. Okay. So if s of A is positive, t has to be bigger than s of A. If it's negative, t has to be bigger than 0. If it's 0, then t has to be bigger than 0 as well. Okay. Now I define R0, which now will depend on little t here as a spectral radius, just like before, of ft times negative v inverse. Okay. Then R0 of t becomes this. So I can calculate it. I'll give a picture of the graph of this function. Proving this is 2 lines. The proof is just an application of spectral mapping theorem from functional analysis, really. Okay, so here are the pictures of that function. So if s of A is negative, t has to be bigger than the maximum of 0 and some negative number, which is right here. So, so it goes from here to here. Hang on. Did I get this right? It has to be bigger than 0, right? If s of A is negative, t has to be bigger than 0. So it started here. And the plot of this function just is a monotone increasing function from 0 goes to 1. If s of A is 0, it's a constant function. That's easy to see. T over t becomes 1. And if s of A is positive, your domain for t is just this. And you get a decreasing function, which asymptotes to 1 horizontally and to infinity when you approach s of A. Here's why basic reproduction numbers are important. It's called a trichotomy. So we can, this is explaining why basic reproduction numbers are proxies of spectral abscissa. So if you have a splitting of our operator, then we have the following equivalences. My spectral abscissa of the original operator A is negative if and only if R0 is less than 1. It's 0 if and only if R0 is 1. It's positive if and only if R0 is bigger than 1. Okay. And why is it so popular? Why is R0 so popular? Because it's often easier to calculate. Despite the definition, it's actually easier to calculate than the spectral abscissa of many matrices. Okay, so let's think about control. Here's what we do in infectious disease. When you read about COVID and how we're going to fight this disease, you may occasionally see, oh, we need to lower R0 from above 1 to below 1. Okay. This is because the reason behind this is you have a disease-free steady state, which you would like to be stable, no disease present. But when the disease is taking off, that's actually an unstable steady state. So by the previous trichotomy, we know that any R0 will be bigger than 1. And so the idea is, well, we should make it less than 1, then my disease-free steady state will become stable. But often it's impossible. It just our options are limited, and we can't make R0 less than 1. And what I want to show, perhaps less important for this crowd, is that that's a dangerous strategy. If you're unable to stabilize, you may, by controlling the disease somehow, you may be decreasing R0, which is what you think is a good thing, but at the same time, S of A the real quantity of interest is increasing. Okay. Okay. So here's the model. The CRN model has 4 parameters, alpha, beta, gamma, and K, positive constants for now. As a disease-free steady state, beta over alpha, just set I equal to 0 and solve for the steady state, and you'll have this steady state. And now you linearize there, you linearize this model, and you get this 2x2 matrix mix. And this turns out to be, this is how it ties to this story that I told you. It's a cross-positive matrix, not on the positive orthant cone, but on the second quadrant of RN. Okay, of course, it requires a little bit of work to convince yourself, but that's possible. Okay, so now I can say, okay, maybe I can split it in 2 terms, F plus V. Well, here's one way. And F and V have to satisfy these conditions that F preserves, the first operator has to preserve the column. So anything, if I apply this matrix to anything in the second quadrant, I end up in the second quadrant. You can check this. V has to be cross-positive on the same cone. You can check that as well. And has to be stable. And here you see it's triangular and the entries on the diagonal are negative. So obviously it's stable. Its spectral abscissa is actually the maximum of these 2 negative quantities, which is negative. So now we can define R naught to be the spectral radius of F negative V inverse. That's just a calculation. Turns out to be this. Very easy, straightforward, K beta over alpha gamma. Whereas S of A is this matrix, its spectral abscissa is the maximum of these 2 numbers. And you can see that the trichotomy, meaning R naught's less than 1 if and only if SA is positive, etc. These 3 different cases holds given these explicit expressions for R naught and S of A. Okay, let's now wrap up and talk about a control scenario. It's not a very specific control, but it's what I think I'd like to argue happened by our improvements in the 20th century in the medical or in the health industry. We live longer, we have better medicine, and so inadvertently we were controlling that system, and because of that, it has kind of odd effects on the simple epidemiology model I gave you. So I'm going to assume that there's some control variable to be unnamed that decreases the death rate of susceptibles. We live longer, so our death rate goes down. The birth rate is going to be constant. How quickly we reproduce doesn't depend on that control. Of course, birth control was invented in the 20th century, etc. So we could argue there that may not be the case, but for the purposes here, I'm going to assume it constant. And then gamma, which is the death rate of the infected people, increases with you. I have to explain why. And then K of U, the infection rate also increases. Okay, so the first part that alpha decreases is because we have better healthcare, and gamma and K increasing I argue as follows. So the death rate of infected people actually increases because we may have more older people, right? We live longer, so we'll have more older people, and they are more susceptible to say the common cold, so they might die, and overall that leads to a death rate that's increasing, and the infection rate also increases. There's more mobility perhaps, and so we get more encounters, so the infection rate increases. What I want to show, and that's the last part here, is that it's possible that your control efforts, right, could be such that you're decreasing or not. So you're decreasing basic reproduction numbers, but you're increasing the spectral abscissa of the operator of interest, namely the operator A. Okay. The proof fits on the slide, so why not? So I claim I can always find a positive constant beta and functions alpha, gamma, and K that have the following monotonicity properties, so that the derivative of R naught is negative, so R naught will decrease, and S will actually increase. Okay. First of all, we have expressions for R naught and S of A. So we can actually plug them in and take the derivatives. That turns out to be those two inequalities are equivalent to this chain here. So here's beta times the derivative of that ratio. And on the left side, I have the derivative of gamma and the derivative of gamma times R naught evaluated at U naught. Okay, so I call this A and I call this B. And note that R naught of U naught was bigger than 1 to begin with. We had a disease present, right? So that means this quantity is bigger than the quantity on the right. The A is less than the quantity B here. Okay, so we have an interval. So all we have to do is say, can I find beta, K, and alpha so that this derivative here is in that interval? And I claim that's quite easy. You can tune your beta, for example, if that product wouldn't be in there, or you can mess with K and alpha. K was positive and alpha is increasing, alpha is decreasing, so that the ratio is still increasing. This is a positive number here. So it's not hard to convince yourself that you can make this thing fit in the interval AB. And that then entails the dangerous strategy R naught is decreasing, but at the same time, you're actually destabilizing more your infectious disease. All right, I'll stop here. I'm already over time, but thank you for listening.